Hello, everybody. This is Mr. Hinnon for the vector multiplication part 2. So this one I'm going to mostly be dealing with the cross product. The cross product is a little bit unusual because you're going to take two vectors and multiply them together, but you're not going to end up with a scalar like we did with the dot product. You're going to end up with another vector. So this picture tries to show this. If I have vector B and vector A here, what's going to happen? So I'm going to run that little video for you. So you end up with it's A cross B, and you end up with the area of this little parallelogram, and it has a direction. So down here in this corner, you're going to actually see there's a direction to that. So A cross B is going to be out of the page, and B cross A is going to be into the page. So it's always perpendicular to the plane of the parallelogram you actually create. So that's what this is kind of dealing with. This is how we draw it. It's A cross B. So you find it by taking the magnitude of the A vector times the magnitude of the B vector, and then times the sine of that angle that's between them. So it's a little bit different than the dot product, the fact that it's sine instead of cosine, and the extra part is this little n vector. So this vector n hat, sometimes as is pointed out, is perpendicular to the plane formed by the two vectors, and it's followed by the right-hand rule. We're going to be using the right-hand rule a whole bunch coming up as we deal with magnetism, because one of the key ideas in magnetism is a cross product. So I want to make sure we have that kind of down. Cross products are distributive, so you can multiply them through, but they're not commutative. You notice A cross B was not equal to B cross A. It's actually the opposite of it. In other words, it points in the opposite direction, so it has a direction that's opposite to it. If you cross something with itself, you'll get 0 because the angle will be 0 and sine of 0 degrees is 0. So all the unit vectors crossed with themselves are 0. But if you actually cross a unit vector with a different unit vector, you're going to get a value of 1, and it's going to have a direction. The direction is going to be perpendicular to those two, and you have to kind of follow the right-hand rule with that. I'm not going to go into the right-hand rule right now, so I'm just going to leave this right here, just because it takes a little bit to get a feel for it, and I'll probably do more of that later, and we'll do a separate one that we kind of get the right-hand rule. The last thing I wanted to kind of throw out is this is if we had something in what we call unit vector notation, in other words, where you have a number times these different units, and I, j, and k are just vectors that point in the x, y, and z direction. So there's nothing special about them. They're just pointed in those directions. When you actually do the cross product, it looks really complicated, but some of the parts disappear. Like I crossed with I is going to actually disappear, and j crossed with j, and so forth. So you end up with this, which you can simplify like this by lumping them together. But this ay times bz minus az times by, that's actually very important. You're actually finding the determinant of this 3 by 3. So if you actually write this is another way we're going to write the cross product with ijk, ax, ay, az, and then bx, by, bz, and that'll kind of work from there. So that's another way to do it. When we get into more complicated vectors, we'll probably deal a little bit with that. So that kind of deals with the basics of it. I want to do a little example here. So I'm going to jump to this page. So one cross product is what we call the torque on something. So if I had a door here and it was pointed in this direction, I wanted to close the door. So I'm going to push on the end. So there's a force that I'm going to act. And then the second part is what we call the lever arm, or the R. So if I wanted to find the torque, I would take force and cross it with R. So the way that would equal is that would be the magnitude of my force vector times the magnitude of my lever arm, or the distance away from the pivot point, and then times the sine of the angle between them. But it would have a direction. So I'm going to talk about that direction in just a moment. So let's put some numbers in here. Let's say you apply a force of 5 newtons on this thing, and you're going to point it basically straight up. So imagine that we're looking down on this door from above. So the idea is we're looking down on the door is kind of tilted this way, and we're going to try to close the door. So we're going to have it close like that. And then R here, just for simplicity's sake, let's say that this is 1.5 meters. So it's going from the pivot point down, and then they form a 60-degree angle there. So if I was trying to solve for this torque, I would take 5 and multiply by 1.5, and then I would multiply by the sine. Now, most people go, oh, it's going to be the sine of 60 degrees. That's easy. But if you get really technical, it shouldn't actually be the 60 degrees. We should actually be putting the two vectors tail to tail. So my force would be like this. And I should actually put the r vector down here to point like this. And the angle I should actually be using would be this big angle right there. But as we can kind of see, this one was making a 60-degree angle here. So if my force was also pointed in that direction, then this angle here is just going to be the supplement of it. They add up to 180. So this would just be 120 degrees. And here's the cool part. If I put in 120 degrees, the sine of 60 degrees is equivalent to the sine of 120 degrees. They're both equal to each other. So that's the nice thing, is I don't have to worry whether I use the 60 or not. And then, like they showed in the video, what you're actually finding would be the area of this little parallelogram right there. So I could chunk that out. Let's see if I can find a calculator down here. There we go. So the first thing I'm going to do is take that 120. I'm going to take the sine of it. So that's 0.866. So that's just going to be the square root of 3 over 2. And then I'll multiply that by 1.5. Then I'll multiply that by 5. And I get 6.495. So I'm going to say about 6.5. And the unit for torque is just a Newton times a meter. And so that would be the magnitude of my torque, but since it's a vector, it has a direction to it. And so the way we find this is with the right-hand rule. I'm not going to go into it too much, but if I was actually twisting the door this way, think of it this way. The door is going to rotate counterclockwise. And rather than say that it goes counterclockwise, instead what we tend to do is we give it a direction, and the direction is based off of the right-hand rule. So we go from the force and we go into the r vector. It would actually point into the board or into the paper right now. So we would actually draw it as going into the paper. So into I would say the floor in this case, if I'm looking down on this. So into the floor. So that would be the direction of it. I'm not going to worry too much about that, and we'll talk more about the right-hand rule and how that kind of fits, but it's always perpendicular. So if all of this is happening in this direction, so I have my door and I'm pushing it up like this, and I'm going to cause it to turn counterclockwise, the direction of it would actually be toward you right now. I was looking down on it. So it'd be, so if this was the door this way and I was closing it, so by pushing on it, by closing it, it would actually be pointed in that direction. So we'll get to that later. Hope you enjoyed this little bit on cross products.